All right, so let's use these two things and maybe some other pieces to understand, to figure out the sizes of the giant component. And in principle, actually, the probability that that we hit a node and it's part of a component of size n. So we'll actually get, in principle, the whole distribution, which is a lot, and that's usually more than we want, but it's kind of great that we can do this. Okay, exciting. Okay. So I want you to hold on, and we'll get the generating function. We'll do this. It's a beautiful thing, and we'll march on to lots of other pieces. But yeah, this is nice. Interesting. Okay. Okay, so again, this is a probability that we have a random node, belongs to a finite component of size n, right? We're going to jump on it. And then, so if we think about that a little bit, so this is our recursion relation. This is a probability that we have chosen a node of degree k. And then this is the probability that the sum of the sizes of all of the subcomponents connected to it. So we're just writing out in words what the picture is, right? What this picture is n minus 1, because you've got one for itself, right? So I want you to understand. So see if you can, we can talk through this. All right, so let's do we're making the statement for it in probability speak. Generating functions, what do we do? All right. So this is a sum of sizes, and we have k of them, right? K of them. So this looks very much like our composition rule. And so, in fact, that's what it is. So let's see. So we have rho, again, is the probability that if we run along an edge, we reach a finite subcomponent of size n. So that's that probability. And then this is its generating function. And we're going to compose that with first the rho thing, and then the generating function for choosing a node of degree k, right? So this is the number of things we're going to add up. That comes from p sub k, and this is the things we're rolling, right? The row sub n's. Seem okay? So this is, and of course we're trying to find the generating function for pi, which is probably that, why would we use pi? We did. But the probability that our randomly chosen node has is part of a component of size n. Again, a finite component. So this is just for the sum of all of the friends' component sizes, and then we have to multiply by x because there's the original node. So that's our tiny little result too. This is the bigger one, and then we have to multiply by that. How do we feel about that?
Big P is the probability that random n of a random link is finite.
Big P is always going to be the probability that you go to your network and you choose a node that has degree k.
Okay.
Yeah. So I had that, I guess, on some slide somewhere, but you've got p sub k and r sub k, right? And these are local, right? This is about the number of friends a node has, and this is about how many other friends a node has. So you've got these two, and then they're allied to pi sub n and rho sub n. Right, so they're p and r. So there's a match in the symbols there, and then we're using n for number and k for degree. That's a k. Right, and then the only one we really know is this. That's what we're given, right?
So that's why we're using these generating functions to make all the other stuff.
Yeah.
Generate all the other stuff.
Generate all that stuff. Yep. We're using them because it's also fun, but because I can see you enjoy it. All right. So this is a structure you will kind of have over and over again. If you have contagion type things, then it gets a little trickier because maybe the first one, is or isn't in fact. Like there's all sorts of other pieces. But this is just about structure, right? Do we have a giant component? All right. So that's pi sub n. Now, the problem with this is the only thing we know in here, right? We know what x is a variable. We know this. We know this generating function. We're handed this. We do not know this one or this one. We're trying to figure those out. So it would be kind of a magical thing if we could get that out of this, right? This is a big mess. So, and in fact, generally, we should not expect to. But the other recursion relation we have is the one, so, you know, a story over and over again is that edges really, you know, it's really best to kind of think in edge space. It's very easy to sort of think about what the nodes are doing, but think about what's happening on the edges, and that usually unlocks a lot of stuff. So again, this is this picture, and we're going to have a very similar kind of generating function connection, but now it's only going to involve a generating function for rho of n being connected to the generating function of rho through R. And once again, we know R pretty immediately from P, right? This is the, yeah. So I should be clear about that. Okay, so just in words again, rho n, right? It's the probably that a random link leads to a finite subcomponent of size n, which is a tricky piece. One step of recursion, right? It's probably that we're going to go along a random edge. We hit a node that has these outgoing edges that reach subcomponents of size n minus 1, right? So they all add up. It's what the picture on the previous slide shows. And this is writing out, so this is a very similar thing as pi sub n. All right. And then the generating function version of this, right? So we're looking for the generating function for the rho, probably that we hit a node that's part of a finite subcomponent of size n. That's sneaky result 1, right? So we're going to sample from this distribution the number of other friends a randomly accessed node along an edge has. So we get 12 for that, and then we go and select from the row distribution 12 times and add them all up. We do it over and over again, or we do it probabilistically, and so that's going to be this composition, right? This is the summing variable, and this is the variable that's being summed. And we'll have another x because we've hit that first node, right? So we have to add 1 as well. So now this is going to be this is a recursive thing for a generating function. You could do another step of recursion if you want, but it wouldn't give you anything new. So we have that this function is equal to some function of itself, and we know what this is, and we have this, right? So it's plausible we could sort this out. And is it going to go away? Well, guess it is. Sorry, shouldn't turn that off. Yeah, that's all we're going to do. All right. So what was I going to say? Well, it's pretty good. Well, let me say, this goes to here, so that gives, oh yes, so I was going to write down this piece that we have, which is f of, the generating function for this one is f of p prime over f of p1 prime, right? The first derivative of the generating function for p divided by the same thing again, evaluated at 1. That's something we derived earlier, right? So fairly quickly we go from p sub k to r sub k. We get those things lined up, but this is harder. Okay. Right, we'll work through an example. We'll work through a little example. What do you think? It's an abstraction way, right? So I mean, this is a bit of a clumsy, messy piece. It's fine, it's true, but this gives us something that we've turned it into this weird ethereal space, and we're talking about functions now, and we should be able to sort things out. Right, so here are our two results. I guess everything's going to start to look a little bit mushy and the same, but we had a pi generating function that's connected to the row generating function through p, right? Because, and this should make sense, we're sampling from a random node, adding up all of the subcomponent sizes around it. This one, where row connects to row, because we're running along an edge, we hit a node, and then we run along more edges. So that's a like-to-like connection. So again, the game is we will try to figure this out, and then we could substitute it into here. So this should, all these things, so stuff I just wrote down. We're going to untangle the second equation if we can, right? I mean, in principle, yes, you could make Stephen Wolfram do it. I really wish he was inside. Anyway, so and then sweating. So the first equation just, if we have f row, we just go boink and stick it in there and we have it, right? And generating functions are funny things. It could be some horrible mess, and then we'd have to sort of undo it with derivatives. But we can find things like, even if you have a generating function that you're not going to undo and find the whole series for, you can evaluate at 1, make sure that's healthy, take its derivative, evaluate it at 1, and that will give the mean of the distribution, right? So you can do some good things like that. We'll want to do that.